3, and I'm really happy to introduce to you all Team 1678, Citrus Circuits from Davis, California in the United States, with 18 seasons of experience, 25 times regional winners, 4 times regional chairman's award winners, 8-time division winners, and the 2015 championship winner of the first robotics competition. So ladies and gentlemen, please welcome David Powers from Team 1678. Welcome to warm up. Yep, we can see it up front.
Okay. All right, ready to go?
Yep.
All right. Hi, everybody. My name is Dave Powers, and this is Brendan. Today, we're going to do our Subsystems 101-678 presentation. So just to give you a little context of who we are, my name's Dave Powers. I am an engineering manager. I work at a company called Advanced Farm Technologies. We make robots that pick apples and strawberries for the agriculture industry. I'm a hardware and design mentor on 1678. I've been involved in FRC this is my 14th year actually, and then this will be my 23rd year around first.
My name is Brendan. This is my 3rd year in FRC. I'm the design lead, and then Dave asked the most important thing I learned, and I said CAD.
CAD. That's great. Okay, to give a little bit of context about what the presentation is going to be. So this presentation is just a little case study and a review from one of our subsystems that we did on our 2022 robot Margie. Specifically, it's going to be the hopper. So the subsystem that transferred the balls from the intake to the shooter mechanism, the pooper, as some people like to call it. And we're kind of going to go through and share some tips and tricks on how to speed up the process of development and talk a little bit about how we go through it so quickly. And then we're just going to share some personal bits through the season that we haven't shared yet. So to give a little more insight into what the hopper is. So I don't know if I can annotate it, but it's this middle bit right in the center of the robot that's below the shooter and above the drivetrain. This subsystem itself had a few major design requirements that we wanted to do with it. So at the beginning of every season, you kind of go through and decide what you want each portion of the robot to do. And this was just our list of major design requirements that we had for it. So we wanted it to be a dual use. We really wanted it to be something that could go through and sort, not only store the game pieces, but sort them. We wanted the system to be automated, so it needed to have some sensors and stuff. We wanted it to be simple, and we wanted it to be reliable. So the image that's up on the screen is our competition version of it. So how did we get to this point? So where did we start? So at the beginning of
Build season.
Is this yours?
No, that's yours, Dave.
Okay, at the beginning of build season, we go through, and Citrus takes the first day. The first half of the day is solely focused on just learning what the game is and how you can kind of play the game. And we really look at all of the things that you could potentially do. We don't look at the things that we are going to do. We don't decide right away what we want the robot to do or how it's going to do it. It's just listing all of the things that it could do. And then we kind of synthesize it down a little bit to what we think the robot should do. So not how it's going to do it, but really what it's going to do. And in this, you can kind of see the end list of all of the things that are circled are the things that the 2022 Citrus robot was going to do. So if you look at the storage portion of it down here, you can see that we wanted to make sure that we could hold the maximum amount of game pieces, and then we wanted to be able to hold them while climbing, which was a small caveat, but that was just because we thought that there was going to be more teams that were going to not climb and that they were actually just going to spend the time shooting the game pieces in the last 30 seconds. Okay, so now the next step, once we have what the robot's going to do, we kind of hone in on trying to use our brains and mostly the internet to try and look at old mechanisms that we've had in the past, or that either we've used in the past or a lot of other teams have used in the past with success. And we're using all of this information to try and decide what prototypes we're going to do to accomplish all of these goals that are listed. So with once we get to this point, we're really just trying to draw out some like really simple, low effort, like as low effort as you can, first prototypes to see how the game pieces interact with each other. And then once we kind of like have done some research and we kind of have filled our brains with a lot of good concepts and stuff, we move on to something next we call it drawing time.
So basically, once we know basically what we're gonna do, we kind of give everyone who does anything related to the robot a chance to like come up with ideas of how we want to do it. So basically, if you see here, every group gets given like pieces of paper, rulers, pencils, and then graph paper, and basically just come up with engineering type drawings for what we want the robot to do and then how we're going to do it. So if you see here, this is me on the right, and then the former design lead on the left coming up with our ideas of how we want to do it. We were very inspired by the 973 robot in 2020 because we saw it as a very simple and efficient way to do the game, and we thought that was kind of like an inspiring way for us to do it. So a lot of the people who looked at the past games were like, we should do a 973 clone as our alpha bot.
Who's this person in the background? It's like he looks like he's very stressed.
I think that's Enzo.
That's funny.
Yeah. Enzo's currently giving up on me.
He's like, I don't know if this is gonna work.
Yeah.
Cool.
I'm a 973 fan. But then so after we come up with our ideas of like how we want to build our robots, we move on to really quick, low effort prototypes. So again, most of the designers were really inspired by 973. So we were like, let's just take that and make it a little bit different so we can use it for this game piece. And then we have a robot on the field, in this case, in 9 days. So we ripped it as quick as possible. We used plywood walls for a lot of it. We used polycarb. We basically just wanted a robot on the field that could do the game like the most base level possible as quickly as possible. So our drivers could get a lot of driver practice because we know that they're a big reason we're going to be winning.
Here's just a couple. So going off of that, some of the slides. This slide is just a couple of videos that kind of show our super low effort prototypes. So you want to kind of talk about how we wrote those?
So these are basically just proof of concepts that we did the Sunday of kickoff, just to make sure that our ideas for the 973 clone prototype would work as our alpha bot. So we're just making sure that, if we put the thing in a polycord, tunnel the polycord, we'll just bring it all the way up, and then we can move from there into a shooter and it'll work well. And we're basically just making sure that our ideas function. So then after that, we can move into alpha. These can be really simple. They don't have to take a lot of time. In this case, we literally drilled holes for a shaft to go through. And then we basically just put long shaft through, put drills on the shaft, and then just spun it around. Like it's really not a case of like no machining went into this except for drilling holes in plywood that we had lying around. In this case, from the last year's tower for scoring. So this is literally just take plywood, drill some holes, and then from there we just make sure ideas work. And then after that, we moved on to our alpha bot, and then from there we were finding failure points pretty much off the bat, just because it was not the most reliable robot. So we learned that C2C was really important because we were having a lot of issues with game pieces basically bringing the balls off of belts because it was too tight in some places and also too loose in some places. So you need C2C.
Explain the C2C.
Yeah. So the center to center of the polycord there, it was basically, they were too tight in some places. So the ball would literally bring the polycord off of the belt. So you can see here too, in this case, that was too loose. So basically as it spun, it basically spun the polycord off of it. So we learned pretty early on, if we're going to do polycord, we're going to have some major problems with it in terms of making sure our C2C is right, which is a reason we ended up not doing polycord in future versions.
Yeah, so I think it's important to know that when it, like this was just a question in there, how do we define low effort? So it's mostly just in my brain, kind of defining it as low, a smallest amount of work as you possibly can do to get something to just see how the concept is going to work. So this one, it's when we say low effort, it's just like really, really simple materials to work with. So like these thin pieces of wood that we can just like drill through, or just like drill holes that throw a bearing in it or something. Like we're not worried about it lasting any longer than like the 5 minutes that we're going to do testing with it. It's basically just like how little time can you put into something and make it and get some answers and learn the failure points that you're kind of going to see. So a lot of the big time with this is the geometries that we're trying to figure out with this. So that's one of the big failure points that we're trying to learn is learning the proper center to centers and the proper materials that or the proper polycord that we're going to use, and how the balls interact with the different wheels that you can use and the different materials. So on this prototype, it's not just going to be we're going to do the polycord and we're try it. Maybe we're going to try and stick a wheel on it or a stealth wheel on it, or like one of the star wheels, as you'll see in the future. You kind of can use this to test a bunch of different things, so you have a really good understanding of like what is going to work.
Yeah. And then so throughout this process, we also found a couple other issues with the failure points. A big one was speed. The ball was either coming out way too slow into the shooter, way too fast. So that helped us find the right speed to bring the ball up. We also found out that to be able to bring the ball fully up and like actually have contact the entire time, we needed a feeder wheel as well, which basically meant that
we're giving a presentation to like 200 people right now.
Yeah.
Sorry, we're actively having a meeting right now.
Yeah, and then so basically we're like, okay, so to support this project, we need a feeder wheel there because the feeder wheel gives the ball that support to then come up through the rest of the system.
I think this prototype this portion of it looks a little crazy because the shooter prototype is also on it, but unfortunately, I missed out on getting the process kind of happen so quick. So we go from this. We go from this version of it, right? And then we kind of, at this point, this is really just like kind of doing some mild 2D sketching to get geometries and then just tracing them. And they don't have to be perfect. So then once we know what the geometries need to be, we'll take all of that drawing and then we'll put it in an on-shape model to get it a little bit more defined. And in that on-shape model, then you can rip these, like we have a nice laser cutter that we use to do this, but you can really do this with just like hand sketching once you have the proper geometries. And your next version of it doesn't need to be as advanced as this. I think we skip a couple steps that most teams would kind of do, but the whole idea of this next version of it is you really just want to build one that's like a little bit higher fidelity. So it's a little bit more defined and it's a little bit closer to what you're going to want to see in the final version that's going to go on the competition robot. So these C2Cs were cut by a machine, so they're within a good tolerance. And these are the wheels that we're actually going to use. And this is the path forward that we're actually going to use. This is Maria.
Thank you.
Okay, so then this next portion of it, once we have this prototype, and like I mentioned, this has the shooter prototype on it, but just imagine it's just this portion of it, just this L. Okay, just that portion of it. We're going to now use this prototype so we can really better understand the limitations and make some mild adjustments to try and get it to the point of where it's going to be something that's going to perform very well on field. So this stuff is really cool because you can then give yourself the opportunity to support yourself in the discovery. And if you give yourself enough time playing with these prototypes, you can define a really good list of reasons why this prototype is good and why it's bad. And in the more important part, I think, that anything is understanding the limits of given the context. When you first build something, you don't really know what it is and isn't capable of. So you're going to want to run a bunch of game pieces through this. And it's a very simple thing, but you're going to want to see and kind of document every little pinch point and where does the game piece get hung up and where does it go through really well and what makes it go through really well and how can we make some small adjustments. And a good amount of your time should be on these like medium fidelity prototypes that really give you a good opportunity to just support yourself in the discovery of all of the things that are going to make it good and make it bad. And then once you have a really good understanding of that, then you can start thinking about like tuning it and making it more making it improve the performance of it, I guess. It really should be in order of magnitude. It's like you build this medium low fidelity prototype, and then you really want to understand and just make it something that's going to be as reliable as possible in terms of accomplishing the goal. And then this goal was take the game piece from the front of the robot to bring it to the shooter of the robot. And if you can get it to perform that like 98% of the time, then that's kind of a good understanding that like, okay, we've pushed this prototype to the point of where we know it's going to be a super reliable system in it. We're going to have to move a little bit quicker. So, okay, so now at this point, we've done a pretty good job with this prototype. And this actual prototype goes on our alpha robot that we do the 5-ball with. So it's hit the point where it's working very well and we're very happy with it. So at this point now we're asking ourselves like, okay, what can we do to get a little bit more out of it? We saw some of the limitations in terms of like speed. It's at its max capability, but it's still not very fast. It still doesn't solve the sorting issue. So all throughout this time, we're doing as much as we can to try and like understand what everybody else is doing and do some research. So this next portion of it, this is a cool video that kind of shows where the idea of the sorter that we had within the hopper kind of was born from. So in this, just a small bit of context. So at AFT, me and Mike and a few other mentors work, and then there's a couple Citrus alumni that work there. And one of the Citrus alumni was big in the VEX robotics world for a while, and he knew of this robot and was very familiar with this game and was like, oh, there was a couple cool robots that had like automatic sorters on it. So he pulls up this video, and it's kind of hard to see in this, but you can see it really quickly. You can see that they intake the wrong color ball and then they just shoot it, they spit it out the back. And we're kind of watching this video and we're like, wait a second, that's kind of brilliant. That's going to solve our sorting issue. That's going to facilitate us. We really are understanding at this point that we think the game is going to be won in the amount of time that you're taking to obtain the game pieces. Like at the high level and like at most levels, it's going to take the same amount of time to like score the game pieces. But if you can get the game pieces faster than anybody else, like you're going to do a lot better. So we see this concept where it has the ball outtake that goes straight through the robot. And we're like, oh, that's a cool concept. We should test that. So we move forward and we kind of get to this point now where we're almost resetting the cycle, right? We have that whole alpha robot done and it's building, but now we want to build a better one. We want to rescope our understanding of what's possible. And we want to build one that's a little bit, has more capabilities. So in this one, you can see this is our third iteration of it. And we actually built in this concept of having an outtake that's built into the hopper. So you can see here, it's just a little flap. Like instead of that being a flat back wall of your hopper, it's just a little flap that is going to open to either let the ball through or it's going to close to make the ball go up to the shooter. And in this one, we kind of made it into our beta robot that you'll see in a minute, but it doesn't really have to be. You can kind of go through the process where you're building a prototype like this version of it, but with just a little bit more capability. Like we could have just built this with the little flap on it and it would have done everything that we needed it to do. So now we're kind of restarting that cycle of like build a really low fidelity prototype, then build one that's a little bit more advanced. And this is our one that's a little bit more advanced. So the rest of the architecture we have a little bit more defined in our brain. So we integrate this portion of it a little bit. So this was the hopper subsystem, and you can see we start getting a little overly aggressive with like mounting our motors lower. And this had the whole structure of what the climber was going to go off of, but it really could have just lived as this prototype to help us discover everything we needed to do. And this could be done out of wood. This doesn't need, we started to do it out of metal because we were running longer and longer practice times with it. And we wanted this to be like, I don't think at this point we understood that this was going to potentially be only a beta robot. Like we thought this could have been the competition robot. So that's when we started doing that. So here you can see it's integrated a little bit more, and this hopper is integrated. We put it on one of our practice drivetrains, and it had the intake on it, and shooter was starting to come together.
And then so once we have like a basic robot that we're like, or even just a prototype, once you have that, you really just want to make it do the thing that it's going to do over and over and over again. So a lot of that just comes down to hours, not minutes. So you want to basically be putting it through its paces for long periods of time. It's when you really start to find out the failure modes you're going to be dealing with, especially doing it in like real match situations. So even if it's like for this indexer, if you just put it on like a cart and then you push that forward into balls and then it just has to sort them, it'll be a really great way to just make sure that what you're doing will work, or what you're doing will be doing what you need it to do well enough. Basically, you want to break it, you want to figure out how it will break, and then you want to fix it so it can't break again. And then once you have like your mechanism and you've run it through its paces, at a certain point, if it's not working, it's just not going to work. So if it's just not going to work, you have to be honest with yourself. You have to be like, okay, this mechanism as we currently have it will not do the job that it needs to do. For this flap, its activation time was just too slow. Like we couldn't get the ball to come out. It would just go up through because the activation time on the piston was just too slow for us to actually sort it correctly. So we had to be like, okay, this functionally cannot work. We have to just scrap that idea, start over again. It's okay to fail. We do it a lot. And we just had to be like, we can't make this work. We're going to come up with a new idea to do the same thing.
Yeah, so you can see in this video, there was a fair bit of latency between the color sensor and the actual mechanism itself. So you can see the ball comes in and then it crosses the color sensor threshold and it gets the reading. And then by the time it fires the pistons and tries to retract it, you can see the ball has already mildly moved past it enough to the point of where this, we kind of were taking a bunch of slow-mo videos and we were like, oh, this is it's not gonna work. So at that point, you have to be honest with yourself and be like, okay, this, you know, I kind of almost don't like the fail faster mantra is like important, but it's not really ever failing. Failing is just learning. Like you're just trying to learn faster. You're not trying to fail faster. Like you're trying to put all of your effort into just facilitating as much learning as you possibly can, as fast as you can. And that goes along with just being willing to like try all of these different things in quick succession. It's really learning faster, not failing faster, but so then, okay, we get to the point where we had done that prototype and we realized that it wasn't going to work. So we kind of went back to square one and we started trying to develop some concepts that we could still use a sorter, but it needed to not have the latency that the flap did. So we were trying to think of systems that could be that could work a lot quicker. And in the video, rewatching the video, we realized that there's no flap on that robot. It's actually just like wheels spinning in different directions. So we wanted to test that. And like when I was talking about the low effort prototypes earlier, somebody had asked the question, like really this is my idea of like the lowest effort prototype that you could possibly do. Like it is 3 drills with 3 shafts and there's 3 holes on this. And it's like we drew like some very basic geometry and then we're just testing to see what the game piece does when it goes through. So like here we are just testing to see if we change the direction of this one, could we get it to sort the ball to go to different. And once you kind of have that in your brain, you're like, okay, that concept works. Now let's build one that's a little bit better, and then we're going to practice with it. So here's our one that's a little bit better. And this is the exact same geometry, and you can see it's got 3 drills on it. It's just 2 pieces of metal now, so it's a little bit higher fidelity. And you can see what we're doing is we're just changing the direction of this this wheel that's spinning. So this is like, you know, you draw some 2D CAD and you can make this out of wood, and you can do most of this by hand, like setting all of your geometries, but we're just testing how the star wheels are working, the different materials on like this kicker wheel, the speeds that we're going to need to run this at. Does just the idea that like passing the ball through there is going to work a little bit more. And then we're just at this point putting a ton of hours into testing all of this as much as we can. in this prototype, really, once we built this, we were like pretty confident that we were going to be able to succeed in our goal of like having this sorter on the robot. And then at this point, right, you get to a moment where you're doing your testing. And I think it was kind of like after we had ran this test, you know, you sit there, you talk with the students and the mentors, and you're like, okay, this is good enough, right? This is going to accomplish our goals. It's good enough. So then we're building the next version of it. So this portion, this robot right here was our practice robot. So the hopper, unfortunately, I don't have a ton of pictures from between when we finished the high fidelity prototype of the comp robot to when we finished this version of it. But here you can see that this is just this basically the same system, all the same geometries, just built into the hopper that's going to live a little bit more defined. And I think this was like week, I don't know, it was pretty.
This was week 3, 4.
Probably week 4 of build season.
Yeah.
So at this point, we've had enough time that we've built the construction of this is very simple, where it's just some flat pieces of sheet metal on some like 1x1s and stuff. But all of the major geometries, like the building of this is relatively simple and goes relatively quick because you know what materials you're going to use for all the wheels. You've done all of that testing. You know what speeds it needs to run at. You know all of the C2Cs, the center to centers, and the geometries that you need to do. And at this point, then it's just putting it all together and helping integrate it and trying to develop a system that's like very simple. So yeah, that's like at this point, you can kind of see how when you're building stuff like this, and I think sometimes it's exaggerated because it's Citrus and we move things very quickly, but move through things very quickly. But there's like no reason that any team can't implement this strategy of just like low fidelity prototype, build one that's a little bit better, and then build one that's even better that can go on the competition robot. Like I really like to look at prototypes as kind of a progression of like you're starting with the simplest possible thing that you can do, and then you're slowly making your prototype get to the point of where it can go on the competition robot. And that's, you can kind of see throughout this procedure that we're just following the roadmap of like build a very simple one to test all of these concepts, and then build one that's a little bit higher fidelity that we can actually use for an extended amount of time. An FRC life cycle is you know, it's in tens or hundreds of hours, not like tens of thousands of hours. So you don't need to like overkill the engineering of it and get an understanding of the boundaries of it. So let's see what else. Whoops. And then at this point, you can kind of really, there's no reason that you need to stop at something like this, right? For us, we are very happy with the hopper prototype, but if you watch this video, you can see there's some things that are still hanging up. Like I think at some point in this video, I believe it's right here, you can see the ball kind of gets hung up before it gets to the singulator. So we're kind of going through and continuing this process throughout the entire year, like literally the entire year until we, at some point, even like hours before we leave for champs, we're always trying to like develop and make things incrementally better. And there's no reason to stop now that there's no bag or there's no like crate and, you know, going to ship. Well, some teams unfortunately have to ship the robot, but you can still do off robot continuation of subsystem, individual modular subsystems, and then bring them with you. And the important thing to realize is like, it may seem like an intimidating process when you watch like how quickly Citrus can go through this stuff, but it's really the only reason that Citrus can do all of this stuff. Like Citrus, the students and the mentors are like no smarter than all of the rest of the teams. It's just building that foundation and then practicing as much as you possibly can. And the more you practice this like low fidelity, mid-grade fidelity competition version of it, the faster you're going to be able to get with the cycles. So like at this point, Citrus has done hundreds, if not thousands of these cycles. And it's just gotten to the point of where it moves very quickly. So it's important to don't get discouraged if it takes a long time to get through some of the cycles when you first start. Just understand that that's part of the process of learning how to get how to be very good at this stuff. And it'll take some time, but you'll get to the point where it'll feel like a very smooth system and everybody will be thinking kind of uniformly in line in terms of testing and doing practice. And then the other big part is you need to make sure that you're prioritizing. So prioritizing this in terms of if you're a smaller team and you only have like one set of designers, you need to kind of decide which subsystems are going to need the most effort at any given time. So like say if you're doing the indexer and like you've gone through a couple versions of the prototypes and then you're kind of putting it together, and then you are only on the first version of your intake and the intake is like the lowest performing aspect of it. You need to make sure that you're prioritizing the subsystem and getting it to a point of where it's going to be good enough. And then once it's good enough, you move on to the next lowest successful thing. And you got to make sure that you're pushing yourself throughout this whole thing. It's not, I think the name of the game in FRC is just iteration cycles and doing things as many times as you possibly can to just like figuring out why it doesn't work and being very honest with yourself of why it doesn't work, and then addressing that problem and moving forward. And you know, it's not about like one person is yeah, it's hard to put it in a way that's not just like you just need to do the work, right? Like it's just sometimes it feels repetitive, but a lot of the times it's just work and being honest with yourself and having a big picture, understanding that, okay, we built this prototype and it exploded and it's like super discouraging. And then you build another one and it explodes and you're like, but like, that's part of it. You need to understand that like every time that something explodes like that, you're a little bit closer to getting to the point of where you can like actually have a really good grasp on what you need to do to make a subsystem work. And that's really important. Cool. Okay, now are we good with some final questions?
Yeah, we do have questions. Well, first of all, thank you very much, David, for the presentation. We really appreciate it. And I'm gonna go right into the first question. Do you have any kind of scheduling in your building process for the mechanisms? And do you have any kind of public document when we can see that planning on the mechanisms?
Yeah, so we as the robot leadership team kind of develop out something called the Gantt chart, which kind of has a baseline schedule in terms of like when we think subsystems are going to be done and kind of a bunch of major deadlines. And when we develop that, we work backwards from our first event, actually our last event, but mainly our first event, in terms of like, okay, we know we need to have 2 weeks worth of time to do practice. So you set your deadline for your, like the robot needs to be completed and with programming on it for 2 weeks prior to that. And it's like, okay, in order to do that, we know that programming needs a week and a half worth of time to do programming. So you bake that in. And then you can slowly go down the line to develop out a schedule. Citrus has some resources, and I can have, at the end of this year, we're going to release kind of like a build blog style thing, and it'll have all of our like schedule related like Gantt chart and stuff baked into it. So I don't know if there are any resources that are currently available to look at, but I can probably, if somebody shoots me an email, I can share the specifics of what this season is going to look like for us.
Okay, well, the next question is, it's not precisely about the mechanisms, but for how long do your drivers in Citrus circuits practice before the regional events?
Okay, so this number is nuts. It's probably like 150 to 200 hours worth of like robot on driving. And we do that because we built that alpha robot in 9 days. And then at that point, we're running driver practice for at least an hour, if not 2 hours, every single time that we're meeting. And we're kind of taking the opportunity with the alpha robot, and we'll do a bunch of driver practice with that so we can better understand how the game's going to get played. And then once we have the beta robot built, or the practice robot built, we'll start practicing with that. And then once we have the competition robot, we'll do some shakedown with that. And we're really, when we're doing this practice, it's not just like robot on driving around, like picking up, shooting balls. We simulate practice matches. So we'll have a robot, more than likely a swerve defense robot playing defense. And then we'll run through like the autonomous, we'll run an autonomous mode, we'll run, and then the full teleop period with an end game cycle. So we'll go through and we'll try and document the whole process of it. And we'll have somebody that's recording it and somebody that's keeping score of it. So we know exactly how much we're improving in every cycle. And I think we run, I don't even know how many practice matches do you think we run?
I think before port, the number was in the 200s.